Well, I'm happy to announce Felipe de León Saenz. He's from here, IMPA, and he's going to talk about polyhedral tilings arising from linked nets.
Okay, good afternoon, everybody. Can you hear me well? Yeah? Okay, so I would like to thank to the organizer for the opportunity of giving this talk with this very nice audience. So the title of my talk is Polyhedral tilings arising from linked nets. So my first mission is telling you what linked nets are, what the linked projective space is, why I'm interested in this kind of objects. So I divided the talk in 3 parts. The first part is about the motivation. As I'll tell you, I'm going to tell you what linked projective space are, what the linked projective space is, what's the relation with the schematic limits of families of divisors. The second part and the third part are about polyhedral tilings. How do we produce polyhedral tilings from linked nets? How they allow us to compute some invariants of the linked projective space. So for the motivation, I would like to start with an example. So we have this classical picture of a one-parameter deformation of a curve with a total regular, where the total space is regular. So we have, here I wrote this example, which comes from an article by Esteves, Vitao, and Santos. And they take this triangle curve in P2. So we have in the spatial fiber something like this. And then we look at this deformation, which is given by this equation where f is a general cubic. So we have a picture like this. So the generic fiber is smooth, and the spatial fiber, we have this kind of nodal singularities. Then we take this sheaf on the family, and we see that this has multi-degree, let's say 2, 2, and 2 in the spatial fiber. We can restrict this sheaf to the generic fiber and consider a linear system. And the question is, when we extend this linear system, how many limits do we have? Well, we have infinite many limits. We can compute them by twisting this sheaf and look at the sections of the limited sections as sections of a larger sheaf. So the question they were considering this in a series of 2 articles is, how do we organize this data? So the short answer is in a quiver representation. So the quiver representation that we have in this example is this. So we see that the sections we choose in the generic fiber in this point here, which is the vertex that corresponds with the multi-degree 2, 2, 2. And the other vertices correspond with the multi-degrees of the sheaf after twisting by some divisors. So essentially, the set of vertices is just the chip firing games that Mira showed before. And the arrows correspond to the chip fire of the movement of the chip firing. So the set of vertices we are considering is just an equivalent class of divisors on a finite graph, which is the dual graph of the curve that we have at the beginning. So if we simplify this picture, we are going to see this representation, which is a representation of this quiver with very simple matrices. All the spaces has dimension 2. If we look at it a little bit carefully, you're going to see that we cannot diagonalize all the matrix at the same time. So yeah, we have this matrix here, which is not diagonal, but all the other matrices are diagonal. For the case when we have like a deformation with the spatial fiber with only 2 components, we see that you can always diagonalize. And this is like a phenomenon which is very special from the case with 2 reducible components. So to organize this data, Esteves, Santos, and Vitao, they introduce some definitions, which are the following. They consider this a quiver, which just means an oriented graph, with a finite partition on the set of arrows. And they introduce the notion of admissible path, which is just a path where a certain type of arrow do not appear in the path. And we have this definition of a CN structure, which is the following. For each vertices of the graph, we have exactly 1 arrow leaving the vertex for each arrow type. So in this case, we're going to have an arrow for each irreducible component. Each vertex is connected to each other by an admissible path, and each maximal path is a circuit, which means that this, for example, here is a circuit, which is a maximal simple path. And two paths leaving the same vertex arrive on the same vertex if and only if this function here is constant. With T gamma is just the function defined over the set of Aron types, which for each Aron type associate the number of times that these Aron types appears in the path. So the picture what you have to keep in mind is that we are looking at this kind of quivers. So this is the case for Z2 quivers. And the simplest case is Z1 quivers. Which looks like something like this. And they also show that up to isomorphism, these are the only two possible Z2 quivers and Z1 quivers. And in general, all Zn quivers are isomorphic as quivers. And now I would like to tell you what a linked net are. A linked net are essentially an abstraction of the properties that the representations that arise in the setup of the degeneration of curves, it satisfies. So essentially, we would like to have these three properties. The first property means that if we have two paths leaving the same vertex and arriving at the same vertex, if one of them is admissible, then the maps associated to the path, one must be a scalar multiple of the other. The paths along a minimal circuit is 0. For example, if we look at the composition of the functions associated to these arrows along this loop, it's going to be 0. And this last condition means that the intersection of the path associated with two paths that do not have Aron type in common must be 0. And finally, we have this exactness condition, which just means that if we look at the image, for example, of two vertices that are very close in the sense that they are connected by a simple path, for example, this vertex and this vertex, the image of this map coincides with the kernel of this map. Okay? So we call exact linked net to a representation of a Zn quiver which satisfies this collection of properties. And we say that they are finally generated if they also satisfy this condition, which means that there is a finite set of vertices that determines all the representation. When we have a linked net, we can actually show that there is a canonical minimal set of generators, which is in some sense tropically convex. So every time that I'm going to be working with an exact linked net finally generated, I'm going to be thinking on this kind of minimal set of generators. So yeah, one of the terms by Esteves, Santos, and Vital is that the setup that appears when we look at this one parameter deformation of curves, they actually fit in the definition that I gave before, so, which means that we have a representation in the category of line boundaries, which is given by twisting the extensions. This is a linked net, which is maximal. When maximal means that every map is generically 0 in only one component. And we have another representation, which is given by taking global sections. This is a linked net, but it's not of finite type. It's not necessarily finitely generated. You can see it by applying Riemann roll or something like that. And there is another representation which comes from the linear system we pick in the genetic fiber, which is actually a finally generated exact linked net. And so what we call the linked predictive space is just the quiver Grassmannian of a finally generated exact linked net. So yeah, I wrote it here. The linked predictive space is the quiver Grassmannian of subrepresentations of dimension 1. And what is interesting about these quiver Grassmannians is that they can be used for describing a schematic limit of divisors. How is that? Well, when we have if we take a linked net of invertible chief, which means just an invertible chief for each vertex of the graph, we have a natural map which is, okay, let's take LP, no. We take the linked predictive space. So an element here is a collection of sections. We can map it to the Hilbert scheme of degree D, with D is the degree of the sheaf, to the intersection of the zero locus of the sections. And they show that this map is actually which is a scheme theoretical map, and it describes the limits of the image of the linear system in the generic fiber of the linked predictive space. But they also show that the linked predictive space is a flat degeneration of the diagonal. So this first property, so I'm interested in this first property, and I would like to answer the question of whether this property is actually a property of the linked predictive spaces without this framework of degeneration of curves. So we look at the literature for some answers. The case of finally generated linked nets over a Z1 quiver, it already appears in the work by Esteves and Osterman on Abel maps and limit linear series. They consider this very particular case when we're in a Z1 quiver, all the maps can be diagonalized at the same time. This implies that the linked predictive space in this particular case is a flat degeneration of the diagonal. The case for Z2 quivers also appears in a series of 2 articles by Gabriel Munoz, but he showed that the linked predictive space is a flat degeneration of the diagonal only in the case when it has the so-called simple basis. And then the result was generalized by Esteves, Vital, and Santos to the case of ZN quivers. So for those representations where all the maps are diagonal, we know that they are flat degeneration of the diagonal. But we don't know what happened in the general case. And actually, sadly, I think most of these kind of representations are not cannot be diagonalized. Another related work is its work by Bing Li on images or rational maps of projective spaces. He, in a slightly different context, he studied the reducible components of the linked predictive space, and he computed the Hilbert polynomial of the reducible components. But it's not clear how to manage all the information at the same time, so we cannot compute the Hilbert polynomial in general from the work of Bing Li. So what I wanted to tell you today is that inspired by this work on topicalization of linear series and tiling by polymatroids, we can obtain some answers about the geometry of the linked predictive space itself. So when we have an exact linked net of vector spaces over a field, probably a infinite field, we know that the LPV has the class of the diagonal in a product of projective spaces. So the rest of the talk will be about telling you how do we show this theorem. Okay. So the first part is introducing this combinatorial framework. So I wrote here a definition that probably most of you know already, which is of supermodular functions. Some people call it polymatroids, I guess. Maybe it's for other people it's more common to look at submodular functions, but once we know the rank of the function, we can pass for supermodular functions to modular functions and so on. Supermodular functions has associated polytopes, which are the base polytopes that are defined by this set of inequalities, and they are always subsets of delta n. We also say that a supermodular function is simple when its base polytope has maximal dimension. Yeah. And we have this definition of polyhedral tiling, which means that a set of polytopes is a polyhedral tiling if the intersection is either empty or a phase of both of the polytopes that we are intersecting. Okay, so when we have a vector space, inside the sum of a certain collection of vector spaces. Let me call it UH. This is a sum of vector spaces, H for each, one for each element in H. We can look at the maps, at the projections. And we can compute the dimension, and we can pick a subspace here, and we can compute the dimension of the projection. So when we compute the dimension of the projection, we have a submodular function, which is this one. And the associated modular function is given by the kernel of the restriction map to the complementary of this set. And when we have a collection of polytopes, a collection of vector subspaces of this direct sum, we can ask for another condition, which is to be complete. To be complete means that, complete for omega, to be complete means that every time that I have a polytop, let me say this one, for example, which intersects omega, which is an open set, there is another polytop at the other side of the face. This could be something like this. It doesn't need to intersect in a face. And for producing polyhedral tilings from these families of vector spaces, we use this lemma by Esteves and Amini. This is a very simplified version of their lemma, which work in a very general context, which means that if I have a collection such that all the modular functions are simple, which is complete, and there are non-zero morphisms, which is not necessary. Let me not tell you what these morphisms are for now, but if we have this morphism between spaces such that the polytopes intersect in codimension at most one, then we have a polyhedral tiling of delta n. So we are going to apply this lemma to the case of linked net. And yeah, so for a linked net, we can take a collection. We take the H to be the minimal set of generators, and each space we embed in the sum, just as the graph of the maps to the different vertices. So this gives you a pair of a modular function, a submodular function, all of them with the same rank, all of them are simple, and they give us a regular polyhedral tiling of delta R plus 1. Associated to this tiling, we have this reduction complex, which associated for each vertex a simplex, and the intersection of and a set of vertices is a simplex if the intersection of the corresponding polytopes is non-empty and intersect omega, where omega is always the relative interior of delta R plus 1. Now, let me relate this to the Kuiper-Grassmannians of these representations. So we know from the work of Esteves, Vital, and Santos that the reducible components of the Lie projective space are these images of these rational maps. We know that this is generally canonical singular of pure dimension dimension of the representation -1. So we show that the reduction complex of the Lie projective space is actually isomorphic to the reduction complex of the polyhedral tiling. So the combinatorics of the intersection of the components are actually controlled by this tiling. This is the definition of reduction complex of a linked projective space. We take one vertex for each component, and a subset of the vertices is a simplex if the intersection of the components is not empty. Okay, so just to finish, let me recall you what the Chown ring is. The Chown ring of the product of projective spaces can be identified with this quotient ring, with HV represent the inverse class of an hyperplane on some projective space under the natural projection. So each cycle class in this graph can be written like this. Can be written like this. So this quantity that appears in the sum, which is written degree of n, is called multi-degrees, and they are the intersection point of x with this product of hyperplanes. And we say that a class subscheme has the class of the diagonal if it has the class of the diagonal, which means that all the multi-degrees appears in the class and they are always equal to 1. So to compute the Chern class of the linked projective space, we have to modify a little bit the result by being Lie. So we get this lemma, which essentially says that the multi-degrees of an irreducible components can be 0 or 1. Moreover, they are equal to 1 if and only if these inequalities are satisfied for each non-empty subset of H. Sadly, this description is not polymatroidal. This function may face to be submodular, so we don't really know how to describe this in terms of polymatroids, even though we know that the set of multi-degrees is a polymatroid. So yeah, so to finish, we just have to count the points. So showing that a point appears in the class is equivalent with saying that this modification of the points belongs to only one of the polytopes upstairs in the polyhedral decomposition associated to the vector spaces. These facts just follow from what I told you before. So let me now show you some pictures. This is like the kind of polyhedral tilings we get in the case when the linked net is generated by something like this, like this polygon. So in this case, we get 3 reducible components, and the set of multi-degrees is drawn here. And we have another configuration, which is this. This corresponds to a linear quiver, which can be seen, for example, this point, and this point. We see that, for example, that the component associated with these 2 vertices do not intersect, but these intersect with the component associated to the vertex in the middle, which is actually very big. This is the set of multi-degrees. So we say that the component that associated with the vertex in this part of the quiver are quite smaller than the set of multi-degrees that the component in the middle. Yeah, that is.